Hi folks, my name is Kedar Karmarkar. I am the Principal Technical Marketing Engineer working at Cisco on Software-Defined Access, and I'm here to talk to you about LISP VXLAN Fabric. So we'll go over what it is, the platform support, feature support, the config guide links, and we will end it up with a demo using Ansible playbook to orchestrate a LISP VXLAN Fabric. So we all know what software-defined access is. It is a full stack of using Cisco DNA Center to automate the configuration of the LISP Fabric. It also includes the Fabric assurance provided by Cisco DNA Center, and it also includes ICE for the policy piece. And this has been the traditional way of deploying a Cisco LISP Fabric, but we are also opening it up to automate or either use plain old CLI, or you can use your own homegrown tools with scripts and all that stuff with either Ansible, NSO, whatever is out there that you use to orchestrate the fabric. So you will still be able to customize within the parameters of the software-defined design for the LISP fabric. And if you happen to have Cisco DNA Center in your network, you can still use the basic device and client assurance that are provided by the Cisco DNA Center. You will not be able to get the fabric assurance piece that is provided when you use Cisco DNA Center to automate the fabric. As far as platform support goes, only Catalyst 9K switches are supported for the various fabric roles, and that too, any Catalyst 9300 or upwards, those switches are supported for the fabric role. Anything below that could be like a layer 2 switch, or it could be intermediate switches in the underlay. For the wired feature support, the release that we are supporting this manual orchestration, manual or like without DNA Center, that support starts from 17.9.3 of iOS XE, and there is a subset of features that are supported with this with the CLI solution of orchestrating the fabric as compared to what is provided by Cisco DNA Center. So for example, only Lisp PubSub is supported, only IP transit is supported, V6 unicast and then V4 unicast in the overlay with the V4 multicast with the head-end replication, and native underlay modes are supported. Broadcast is there as well, and also the multi-site remote border, which is the VN anchoring and is popular with guest access. Also, obviously, you will be able to realize the Cisco TrustSec micro segmentation capabilities with .1x and the SGT allocation. Also, from a topology standpoint, basic well understood topologies are supported. Fabric in a box is supported as well. No advanced features are supported. For example, the SDA transit, extranet, L2 only VNI. So those are not supported with this manual option for the LISP fabric right now. But again, if you have any features that you intend to deploy with a LISP fabric, please reach out to your account team and they can contact us and we can work out a solution for that. Wireless support starts from 17.9.4 and again only Catalyst 9800 series WLCs and Catalyst 9100 and Wave 2 access points are supported. Fabric enabled wireless with the appliance, with the 9800 appliance, as well as embedded wireless with Fabric in a box is supported as well. Centralized wireless could be any wireless because there is no tie-in of the fabric with the wireless, so that is no factor. These are the collateral links on CCO. The config guides are here. You can use that to form the command set that you need to deploy the fabric in your network. The troubleshooting guide is published on CCO as well, as you can see. We recently posted an Ansible playbook on the Cisco DevNet GitHub site, so you can use that to again customize for your network, and you can use that Ansible playbook to orchestrate the fabric in your network. So the key takeaway is LISP VXLAN Fabric orchestration is now open. It does not only need Cisco DNA Center, so you can use either Ansible, NSO, or any homegrown tools that you have, or you can use plain old CLI as well. A subset of features from the wired standpoint are supported, so please note that. Integrated wireless support is there with 17.9.4, and then centralized wireless is supported. If you happen to have Cisco DNA Center for doing device lifecycle management, you can certainly use that. You can use the software image management on the devices, device 360, device assurance, and client 360 for basic monitoring. And now it is time for the demo. So in this demo, we will be using the Ansible playbook that's posted on the Cisco DevNet site to orchestrate a fabric. And this is the sample topology on which the orchestration will happen. So here I have a couple of switches. VLAN 2.1, VLAN 2.2 are my access switches, which will be the fabric edges. I have MIG1, MIG2 as intermediate nodes, so there is no configuration happening on those. I've got I1.1, I1.2, which are the core switches in the network. That will be potential fabric, border, and control plane nodes. And then I've got bogey 1 and bogey 2, which are routers, which I will use as fusion. This obviously is the external network outside the fabric. And then I've got shared resources in the 192.168.4.0 network, say like DHCP, that I will route leak into the VRF so that they can get DNS, DHCP, and those basic services. I've got the Ansible stack also in this network in 192.168.4.0 network. Right now the underlay is all configured, so the loopback 0 of the switches are all reachable to the Ansible station. And so off we go into the demo mode. So let me minimize the screen and then show you the switch consoles that are there already. So this is VLAN 2.1, my edge switch. As you can see, there's no VRFs, there's no LISP, and there is no configuration on 101. Same thing here on the second edge switch. On the border or the core switch, which will be my border and control plane, again there is no VRF, there is no LISP on both these two switches. And then on the routers there are no VRFs as well. So it's again basic plain underlay configuration which is there right now. So let me show you what the Ansible components look like. So this is my folder. I've got various files in it. I'll start off with the inventory file. So in this file I have the name of the device, the IP of the device, and the role. So in this case I've got bogey 1 and 2 with their IP addresses, and their role is fusion. I1, 1 and 2 are border and control plane nodes, and then VLAN 2.1, VLAN 2.2 are the edge nodes. In this file, I basically define the border BGP autonomous system number, which is 65001, the fusion BGP AS 65003, the global prefix, the shared services prefix that I will route leak into the VRFs, and then these are your LISP instances. So the 4097 maps to the GRT, which you all know as infra VN if you are used to the Cisco DNA Center orchestration. Again, I'm mapping VLAN 2, which is 164.3 to 8097, which is the L2 instance. And then I have got two VRFs. So instance 4110 maps to VRF V1, and then VLAN 10, which is 10110, maps to 8110 L2 VNI, and then VLAN 20, which is 10120, maps to 8120. And on this specific subnet, I have flooding configured. So these are the commands that will be deployed for supporting the flooding on this specific VLAN. 4130 instance maps to VRF V2, and then VLAN 30 maps to say 10130 and maps to 8130 L2 VNI. So these are basic network parameters that I have in this folder. If I go to the host specific configurations, these are my port assignments that I define on my edge switches. So in this case, you can see that I can use individual ports and map them to VLAN, or I could use port ranges as well. So this is my border handoff, my IP transit handoff from I11. So in VRF V1, I've got two handoffs to bogey 1 and bogey 2. So I'm using 2001 VLAN with a prefix of 2.1/30 on this interface going to bogie 1, and then the same thing for bogie 2, and the same thing for the two handoffs in VRF v2. And if I show you the file for the fusion, it is basically a reflection of the above, right? So again, basic network parameters that I'm using in this one. If you go into playbooks, these are obviously the different YAML files that are there that we will use in conjunction with a single command. I've got the Jinja templates in the template folder, and then the files folder contain the output of the command set that is delivered to the switches. So right now what we are going to do is we are going to fire off one Ansible playbook, and that will take us through the journey of not only setting up the fabric but also automating the IP transit handoffs to the fusion, automating the handoff on the fusion as well as the route leaking of that global prefix into the VRFs, right? So off we go here. So as you can see, once I fire it off, the script will start checking the variables and then logging into the boxes. So it is creating the border config on my I1, 1 and 2, which are my core routers. It's gathering the loopback interfaces of the fusions and the borders, and then creating the border pub/sub config. So as you can see, there is activity happening on both the borders here. These are my IP transit handoff interfaces for VRF v1 and v2. That's I1 1 here, and then I1 2. Here it is basically going through the overlay configurations on the fabric edges, VLAN 2 and VLAN 2.2, and then configuring the flooding and all that stuff on, like configuring pub/sub on the edge. It's now creating the BGP fusion configuration on the fusion devices, which are my bogie 1 and 2. And that's it, it's all done. So the script has executed with 0 failures here, as you can see. And then as you can see here on the fusion devices, I've got the VRF handoffs coming up, the BGP neighborship coming up on the fusion boxes. So let's begin with the edges, and let's see if our Lisp session is up with the border and control plane. So they are up, 164, 1.5 and 1.6. Let's do a show VRF, and as you can see, the VRF v1 and v2 are created, 2 subnets in VRF v1 and then VLAN 30 in VRF v2. This is the show run interface VLAN 10 in VRF v1. Same thing for VLAN 20, and then same thing for VLAN 30 in VRF v2. The Lisp configuration, as you can see, these are my global parameters of the configuration for the service IPv4 section, and these are the instances that are mapped to the VRFs. So 4097 maps to global routing table, and then 4110 instance ID maps to VRF v1 with 2 subnets in there, and then 4130 maps to VRF v2 with 1 subnet in there, 10130. And these are my layer 2 VNI configs. 8097 maps to VLAN 2, 8110 maps to VLAN 10, 8120 maps to VLAN 20. And as I mentioned before, the flooding support that I've configured only for VLAN 20, that's all there. And same thing, instance ID, 8130 maps to VLAN 30, right? So this is all again basic standard stuff, Fabric Edge config. Same thing on this VLAN 2 to VRF. The one thing I'll show is this interface has now been mapped to VLAN 10 on both the Fabric edges, and that is again the same configuration on the Fabric edge. Again, both my sessions to both the border and control planes are up. On I11, we can take a look at the VRFs. So again, these are the loopback that we use to advertise the overlay prefixes. These are my handoff VLANs that I use with the Fusion devices. And I can do a show run section Lisp. And again, this is the global parameters for all the different VRFs. This is the control plane config for VRF V1 and V2 and the default instance of Lisp. And even the BGP configuration is now automated, again created for VRF V1 and VRF V2 on I11. Same thing here on I12, the second border and control plane. And this is again the standard Lisp configuration, the border and control plane configuration that was deployed. And again, that's the VRF handoff, BGP handoff to the Fusion, and then V2 as well. Coming to the Fusions, where there were no VRFs, now we have the VRFs and their handoffs. As you can see here, I can do show run section BGP and show you the handoff section for VRF V1 and V2. The other thing I mentioned about the route leak. That was supposed to happen on the Fusions. So as you can see, I've got those commands, import and export commands, to import the global shared services prefix in the VRF and export the VRF prefixes into global routing table, right? So as you can see, this is the shared services that is being route leaked into the VRF, and these are the VRF prefixes that are exported out to the global routing table. And that's the same configuration on Bogey 2 as well. Right, so if I check on my I11, let's check the routes. So I'm receiving a default from the upstream neighbor. So this will register this border as a default border. And also you can see I've got the shared services subnet that is route leaked into VRF V1, and the same thing goes for VRF V2, right? So now let me bring up the IXIA, which is connected to the two ports here, G101, and we will have a host. We will have a couple of hosts connected to both the to both of the edges, and we will ping the external DHCP server which is outside the network, and the other host which is inside the fabric. So let me initiate some ARP resolutions here, so the hosts get registered into the Lisp fabric. I think those should be good. So it takes a couple of seconds just to get that. So as you can see, I've got 10.1.10.202 on VLAN 2.1, and then if I execute the same command on the other edge, you can see 10.1.20.201. That is there on this one. As you can see, my default borders are also registered in that instance on both the edges. And now let's see whether the border control plane has that information. And as you can see, I've got both the /32s on I11 and on I12 as well. So now let's initiate the ping and we'll check what is the result. So from this, I'll send a ping to the external entity first, and as you can see, I've received a response. I'll send one to 10.1.10.202, and as you can see, I've received a response as well. So as you can see, it's easy again to configure the LISP VXLAN Fabric, and it's much more easier when you automate all that stuff from the Ansible playbook. So I hope this has been useful use of your time, and have a nice one, everyone.